Our first session is on managed runtimes, and our first speaker is Alen Stojanov from ETH Zurich, and he's going to be speaking to us about SIMD Intrinsics on managed language runtimes.
Thank you very much for the introduction. So this is a work done between me and Ivan Toskov, who recently graduated at ETH Zurich, then Tia Kron from Purdue, and Marcus Kuschel also from ETH Zurich. So let's start with the presentation and let's go in directly into the motivation part. So managed languages, they're really cool because they're general purpose, they are robots, they're portable, and they offer high level features when we develop code. On the other hand, they lack low-level control, and they lack access to machine-specific instructions, which in many cases are very important for achieving high performance. If we go on the other side to low-level languages, we see an opposite situation where we are capable of developing fast code because we have access to architecture and microarchitecture specific instructions. But on the other hand, we're still missing the high-level features of a language that are usually important for productive development. Then we start with the question of, can we reap the benefits of the both worlds? So in this presentation, I will argue that yes, it is possible, and we will attempt to support SIMD instruction in managed languages. So what is SIMD? Well, I guess for this audience, this should be pretty clear. SIMD stands for a single instruction, multiple data. In other words, if we have to perform addition to 4 elements in this 4 consecutive elements in memory, once we perform scalar code, we actually have four additions. And if we go into the SIMD world, we actually have a single instruction to perform 4 additions. How can we use the intrinsics? Well, when we write scalar code, we just run a for loop and just many additions. And once we go to the AVX world or SIMD world, we actually use these specific functions which are called intrinsics. The interesting thing about intrinsics is that they usually map directly into one or several instructions. So in the case of scalar, we just have a scalar addition, and in the case of SIMD world, we actually have vector addition. There are plenty of SIMD instructions, and they're organized in different categories, starting from MMX, SSC, AVX, and so on. So if we look at SSC, what we see is that SSC instructions work on vectors of 128 bits of data, and they can process 4 floats or 2 doubles, and anything from 2 to 16 integer numbers depending on the underlying bit size. Once we go to AVX, the length doubles to 256 bit. Now, if you think about all these variations, and if you consider only 3 operations like multiplication, addition, and subtraction, you can just imagine how many different instructions we will have in order to support all of these different types. And note, those 3 operations are not the only thing that we have to deal with. We have shuffles, we have string operations, we have bitwise operations. We can do cryptography with SIMDs, we can load and store, we can perform casts, and so on and so forth. So trying to quantify how many of these we have, we can see that only SSC and AVX individually and cumulatively contain more than 400 instructions. Then there is Night Corner, and there is the simple vector math library from Intel, which is also packed as an intrinsics function. Note that this graph does not even include AVX 512. And the reason for that is because it won't make sense. Only AVX 512 has 3,500 instructions. So the question is, if we want to include them in certain managed language runtime, how do we actually do this? So I had an amazing idea. I get a master's student to do it. And actually there was one brave soul that took the job, and we discussed the idea, and it turned out that that's a lot of work. So doing this manually, well, we wouldn't do this. It's tedious, it's boring, and most of all, it's error prone. So the second idea was, let's try to generate those automatically. So if you ever develop SIMD code in your life, you are probably familiar with this nice website offered from Intel, and it's called Intel Intrinsics Guide. It's a nice web interface. It lists all the intrinsics available from the Intel compiler and also GCC compilers and many others. And it comes with descriptions of each one of those functions. The interesting thing, if you look at the code of this interface, is that it comes with a nice data XML file, and this XML file contains the specification of all intrinsics. So we decided that maybe we can use this file to include those intrinsics. But then the question comes in, what do we actually mean by including these intrinsics? So let's be slightly more specific. Our test bed, what we tend to do would be Java and actually the JVM. The very first intuition is, since Java and JVM support the JNI or Java native interface, can we just simply use the native interface as that we call each intrinsic function because it's actually its function after all? Well, no, we don't want to do that because every time we invoke a JNI call, we have to pay a price, and this is because the call to JNI is slightly pricey. So we got rid of that idea. The next idea was, how about we try to modify the JVM? Such a work was done before. Long time ago, there was the Jituno JIT with Java vector interface. Then there is the ongoing work with Panama JVM, which supports interesting amount of intrinsics, but maybe not all of them. And there's GraalVM that could potentially support intrinsics, and this is if the Oracle developers decide to do so. But we didn't like this approach because it seemed like a lot of work. So we had actually a very different idea in mind. So we want to use staging. We wanted to go to the Scala world and use staging by writing embedded DSLs and using lightweight modular staging to actually perform this task. So now comes the question, what is staging and what exactly is LMS? So let's consider a very simple example. Consider this function which adds two floats. If we execute this function on the Scala language, what we're going to get is normal CPU execution, and the result of adding 2 and 3 will be output, which in this case is 5. If we go to the staging world, and in particular LMS, we can hop in this round by just switching the types from floats to rep of floats, or representation of floats. Then, once we execute this piece of code, instead of obtaining the result, we have delayed execution, and AST is created. So the result of adding 2 and 3 is basically a node in the AST, which represents the addition of 2 and 3. So why is this cool and why is this important? Well, if we look how staging DSLs look like, we can still have a practical example with this small code snippet. But let's make it a little bit less efficient by adding this small inefficiency. So if we stage this, what we obtain is an AST, and we can actually modify this AST. We can rewrite it and optimize it, and naturally we can optimize this operation. Essentially, once we have done all the optimizations, we end up with a compact graph that we can unparse to the C code, and our job is done. So now once we introduce the scale of the intrinsics and we know what is staging, the question is how do we make use of this process in our task of porting the intrinsics? Well, our approach is in fact twofold. In the first step, what we perform is that we take the data XML file that I mentioned before, we parse it, we generate a bunch of DSLs. And each DSL that we generate is an instruction-specific architecture DSL. Once all DSLs are done, we can actually go and use this DSL inside the JVM. So we develop code using the SIMD DSLs that we generated offline, and inside the runtime of the JVM, we will generate, compile, and link our stage code in the JVM such that we can use it directly. So let's see how this procedure works. The XML file that comes from the Intel Intrinsics is quite convenient. So it contains a description of all the Intrinsics functions. It specifies the ISA, and it also specifies input arguments and return type. So we can actually use this to generate these functions. Looking at this process, it's actually subdivided in several sub-processes. The four of those, the four most important being those here. So in order to actually create elements DSLs, what we do is we actually follow these 4 steps. And the first one being that we define all the nodes of our AST. They are just simple classes in Scala. The next step is that we have to define all the staging functions. And LMS is quite nice because it allows us to do this in such a simple procedure, which does many things in the background among the SSA. Next thing is that we write a default transformation step, which is called a mirroring routine. And once we're done with everything, we have another routine to unparse the code into C. So there are certain challenges in achieving these DSLs. The first one is that not all the instructions that we have are immutable, because what I described before will work great for immutable operations. But once we have mutable operations, they might create read and write effects, and we have to process those read and write effects. So the interesting thing about the same XML is that we have the category for each instruction. So if the category is a load or a store, we can already figure out the effect that is being created by LMS, and we can generate code accordingly. Another challenge is that once we have to write this mirroring routine, we notice that the methods become too big because we have to pattern match against many objects. So we already hit a wall because we were above the 64 kilobytes limit. To avoid that, we just simply split the DSLs into smaller classes with smaller implementation, and we created a trait that will inherit all of them. Then there were other smaller challenges. So Intrinsics, they can operate on unsigned types, and the JVM does not really support them. So we used Scala unsigned instead. Then another challenge was the use of pointers. Well, JVM does not support pointers, and we didn't want to go through the hassle of all these pointer arithmetics, so we simply decided to disallow them and use memory offsets instead. Another challenge would be, do we focus on arrays only? Because if we go down to the C world, we might have heap arrays or stack arrays. So in order to avoid this challenge, we just decided to abstract the containers according to the needs of the DSL. Once we were done with all of those things, we ended up with this nice repository that is currently hosted on the GitHub page of Ivalo Toskov. You can actually check it out, and there is also a Maven artifact submitted. So now comes the question: once we have all these DSLs, how we can actually use them? How do we in fact write SIMD code? So the procedure is again this: we're gonna reuse the pre-generated EDSLs, and we're gonna generate and compile the code. This step has actually several sub-steps, actually again 4, and we're gonna iterate those by implementing a simple SAXP code. SAXP stands for a routine that will add 2 vectors such that the second one is multiplied by a scalar. The very first step that we start in our development is we need to create a native placeholder that will fit the SAXP native function. Once we are done with this, the second step is that we create an instance of the ISA specific DSL. In this case, we just want to implement everything with AVX, so we instantiate an AVX EDSL. Then comes the third and the most important step of actually developing the code for the SAXP function. You can ignore most of it, but the most important part is that we have a loop, we load, we perform fuse, multiply, add operation, and we store the results. After we're done with the implementing, what we have is just a call to a compile routine, which will compile our code. It will automatically link it, and we can use it inside the JVM. This is basically this process that is done by a single call to compile. In fact, it has multiple steps, but we will, for the sake of this presentation, we don't have to cover all of them. So why is this useful? Why is this cool? Let me give you a rather more complicated example of matrix multiplication. You don't have to understand the code, but what is very interesting to see is that how we can implement matrix multiplication in 14 lines of code such that we use various features from the Scala language. For example, we can use the Scala collections and iterators right away. Then we can use pattern matching directly. I wish I could do this in C. Then we can use closures and many other features. So this is the beauty of using elements to perform this job, because we kind of get an abstraction with no regret. The question that comes is how good we are with our approach. So let's look at our first example, the Saxby function, and it will look like this. We performed our test on an Intel Xeon machine, which is Haskell enabled. We use an Intel C++ compiler, we focus on Java 1.8, and we use Scala meter to actually test our performance. What you see on the x-axis is the size of the vector, and on the y-axis we have the performance measured in flop per cycle. We test our Saxby implementation against the Java implementation. And what we can see is that the performance of our implementation is not that different from the one in Java. The reason for that is quite simple. Saxby by definition is a memory-bound problem, so even if we write this with scalar functions, we might expect more or less the same result. But if we go to the same matrix multiplication, the situation is slightly different. The code for matrix multiplication is exactly the one that I showed you, and it's tested against two Java implementations. The one being the standard triple loop implementation, and a blocked version of the same code. So as you can see, we have quite some improvements over the initial implementation, and there we see the benefits of using SIMD Intrinsics, particularly in the cases of code with high operational intensity. Another benchmark that we did, which was very cool, was we used quantized arrays. So quantized arrays, and we actually performed the dot product on different quantized arrays. So the quantization is a process where we actually reduce precision for the sake of speed in computation. Is used in various machine learning approaches, algorithm like stochastic gradient descent. What we benchmarked was 4 versions, 32-bit, 16-bit, 8-bit, and 4-bit precision. We have developed our LMS implementation, and we benchmark it against equivalent Java implementation. So here you see the real power of going very native to the instructions, because Java, when it's processing lower bits, it has to perform cast all over again over the code. And we observe about 40x improvement once we do everything with our own native implementation. So all of our code is publicly available to my GitHub page. It's called Engine, and you can actually download it. You can check out our experiments, and you can try to develop your own code. So to summarize everything, what I've showed you in this presentation was a systematic generation of SIMD embedded domain-specific languages. I showed how metaprogramming and staging can give back control to the programmer to actually write very efficient and very specific code. This work also shows how low-level instruction can be put inside the managed language runtimes. And finally, we showed how we can perform abstractions without regret. Thank you.
Questions for the speaker?
Yeah.
Thanks for the talk, Dr. I was wondering, you were mentioning an advantage of managed languages is portability, right?
Yeah.
These instructions, you give that advantage up, right?
So I can quote Christoph Dubak on a previous keynote that was given yesterday. He postulated performance is not portable. I would say performance is maybe not portable. So the idea here is that the only requirement that we have on the machine that we are running is just install the GCC compiler. So that's the only requirement. So the moment that CLang or ICC, the moment one is available in the path, the runtime will figure out everything. But yes, I agree this is a limitation.
So would you say that it's more targeted for example, for library implementers than for like the end user of the language? Because
you can perceive this from two perspectives. So the package of elements intrinsics can be used for any kind of code generation, just like to do your own compiler interface. The runtime, well, it could be used for both, for target developers and as well for library development.
I was wondering the examples you showed against Java. Like from the perspective, should the auto-vectorization of the JVM as well trigger in those cases? Did you look at that?
Yes. So what we have as a baseline is a for example, in the matrix multiplication case, is that we have a triple loop. It's the slowest baseline ever. You know, the auto-vectorizer cannot really do much. The interesting thing here is that various implementation of the JDK can provide different levels of vectorization, right? So we observed, particularly in the case in the dot product, that JDK 10 might do one thing and JDK 9 might not do the same thing, right? In our observation is that with the code that we provided, and this is basically a dot product that accumulates integers, the auto-vectorizer on Java 1.8 wouldn't do much. That doesn't mean that the case will be like this in a subsequent implementation. But after all, our job is not to compete with the JVM. We don't really want to do this. We just want to show that our approach works and that benefits are immediate. Yeah.
Can you go back to the previous slide? That's the matrix multiplier, right?
Yep.
And so the bottom, kind of like your reference version, your reference implementation is 1.3, then you lose the way you like write down matrix multiply if you're just like copying the formula into code.
Yep.
That doesn't include any intrinsics, any SIMD?
So what we did, and it's also available in the paper, is that we actually tried to output the assembly that was generated in the triple loop and in the block version. And unfortunately, in Java 1.8, we didn't really see vector instruction coming out. If you rearrange the code and if you hack it and maybe you perform array copy such that you avoid the aliasing that the JVM cannot prove, the JVM will actually be able to vectorize it, and maybe you will get a baseline that is somewhere in between. Actually, this was attempted before, but that's it, right? The thing is, like, we don't have the fastest baseline in the Java world, but neither we have in the elements intrinsics. If I do every optimization by the book for matrix multiplication, I can reach 32 flops per cycle, theoretically. Yes?
How do you compare with the same implementation in C, for instance?
Depends. There is a calling overhead when you call a certain function, right? In general, depending on how many iterations, how long your experiment lasts, you might see a discrepancy or you might not see. The interesting observation here is that the JNI overhead, you just pay it only once, and that's it. Now, the thing is, like, with the JVM can do many different things. So when you request a certain memory space, the whole JVM goes into halt because the GC should not be removing this memory region, and a copy might happen, right? So those are legitimate problems or limitations that we have and are imposed by the JVM itself. In reality, if you have high operational intensity, even copying the whole data will not impose so much problem compared to the JVM. However, the native implementation in pure C will always be faster.